Okay, so today what we are going to see are olefination reactions. So the olefination reaction in a very general scheme. So what I'm going to do is to follow the PowerPoint that is online from the website of Professor Bunz, and so if I'm going too fast or whatever, you can find all the information there. So I will anyways explain all the mechanism as is normally done in these lectures, but yeah, just in case, and if I'm going too fast or you don't understand something, just please feel free to ask me. So the refinaction reaction, the general scheme is shown here in this slide. So it's just the reaction of a group which contains a living group, which is normally an an halogen, which is converted to a special reactant. We'll see that this reactant depends on the type of olefination that we are going to use, and the reaction with a carbonyl group, and at the end of the lecture we'll see that it's also possible with carboxylic centers to give finally the formation of a double bond. So the different olefination reaction that we are going to see today, I'm just showing you here the scheme. Will be the Wittig reaction, Horner-Watford-Emmons reaction, Peterson olefination, Julia, Lithgoe, McMurray coupling, and Peta-Cis-Tebe olefination. So for all of them, so they use a different reagent to react with the carbonyl compound, as we will detail in each case. For every reaction, we will talk about the mechanism, the stereochemistry, and also I will show some experimental examples of each of them. Okay. So Wittig reaction. So the Wittig reaction is actually follow this scheme here. So I'm going to explain. I will explain in the following slide the mechanism in detail, but in general terms, it consists on the reaction of a derivative which has here X can be an halogen or tosylate, so can be a good living group with a carbonyl moiety in the presence of base, of course, and previously formation of the phosphonate, where the substituent of the carbonyl group can be alkyl or aryl. So let's go deep into the details of the mechanism. So first of all, the Wittig reaction. So the Wittig olefination starts first of all with the synthesis of the phosphonate of halide, which is the reagent used for this kind of coupling. So the synthesis of the halides is first of all take place from a reactant which has, as I said before, so here a good living group. The reaction with then with triacyl phosphine 3. Okay, so here, so the phosphorus has a lone pair now here, which is the oxidation state of the phosphorus here. Who is up for 3? Hands up. No one. For 5? 0. 0 cannot be. Phosphorus. Okay, so phosphorus 3. Okay. So the phosphorus also has a lone pair which is available now for the nucleophilic substitution of this center here, giving rise to this intermediate. Now we have a plus charge on the phosphorus. Okay. And now finally the formation of the halide takes place with the use of a base. So this center here, so this carbon here, of course, has also another proton, which is especially acid because the corresponding anion is stabilized by resonance, and also is stabilized thanks to the d orbital of the phosphorus. So what I mean is there can be an interaction, stabilizing interaction between, so if we draw the orbitals, it would be the d orbital from the phosphorus, and this would be from the carbon. So it's possible an stabilizing interaction between the p orbitals and the d orbitals of the phosphorus. So okay, the deprotonation then of this intermediate gives rise to the highlights. It of course has a resonance structure which is like this. Sorry, this 1 8. Okay, and this is called highlight. Now this highlight can react with the carbonyl group, okay, in two different ways. So we have if we draw here the structure of the next carbonyl group, so it can react in two different ways. So if this is the plane of the highlight, okay, so the carbonyl can react either like this or either in the other from the other side. So it's like one side of the plane or the other side of the plane. I will explain the stereochemistry in the next slide, but just I want to first of all draw the whole mechanism. So that would be the highlight, the nucleophilic attack to the center to give so okay, so this intermediate. So this intermediate in this case is called beta 1. Beta 9 and evolves to give the oxaphosphatane. So which is, of course, we have here is we have a plus charge on the oxygen and a negative charge and a plus charge in the phosphonium, and then so it's just the collapse of these two charges. The last step of this mechanism is finally the rearrangement. There is a rearrangement to give rise to the final double bonds. So there is like this in both cases, giving rise finally to as we can see here, so the final result of the different pathways are give different isomers. So one is the E isomer, which is minor, and the Z, which is the major in this case. So okay, so this is how the mechanism take place, but it's important. I would like to refresh first of all before explaining how is the stereochemistry determined in this system. I would like to explain you briefly about an aspect about the reaction. So the reactions, every reaction are considered to take place to proceed either via kinetic control or either thermodynamic control. Both processes, so both routes, the same reaction can differs from the reaction coordinate, which means the energy of the process, and we'll have, so first of all we have, I write it here better, so we have the kinetic control, okay, so both processes differs in the coordinate, reaction coordinate. So if we draw now, we represent the reaction coordinate and the energy. Okay, so the kinetic control is the one that take place, is the pathway that take place through the less activation energy, and then gives rise, but however gives rise to not a stable product as we can get with thermodynamic control. Here with here, the activation energy, activation barrier would be here. So this, the formation first of all of a transition state, and finally the kinetic product. On the other hand, so the thermodynamic control of the reaction, so is a process that takes place through the highest activation energy, but however gives rise to the most stable product. So if we draw now the energy of the process, the reaction coordinate, we would have something like this. And now the activation energy will be here, this one, which will be higher. Okay, this is very important because this is going to determine in all types, in all the reactions that we're going to see, it's going to determine the stereochemistry of the process. So kinetic control, then kinetic control is happening in very highly reactive region, so therefore it reacts very fast, and then the steric hindrance has a crucial role. Okay, for the thermodynamic control, however, so the reagents have their time, so the reaction that happen slower, and the reagent rearrange in such a way that finally they prefer to give the most stable product, so the most favorable product in terms of energy. Okay, there is also something that I would like to highlight, which is important to understand the rest of the explanation about the stereochemistry, is that in a multi-step reaction, if we have now we draw the So in a multi-step reaction, if now we have several processes that take place before the obtention of before obtaining the final product, so the rate limiting step will be the one which has the highest activation energy. So for example, here we have the intermediate one creation and then giving rise to the product. Okay, so we would have like activation energy, activation barrier will be this one, the first one, and the second will be obviously this one here. So the rate limiting step would be the second. Okay, these here are the starting materials, and this the final product. Okay, is that clear? Okay. So in the rate limiting step in the Wittig reaction is actually, if we come back to the mechanism, the rate limiting step is the first one. Rate limiting step. So why is that? Because the halide is true that they are stabilized, so it's favorable to deprotonate the phosphonium salt, but there is a species which is highly reactive. And as I have explained, highly reactive species then prefer to react fast, so then the steric hindrance plays a very important role. And so to see the factor that impact the final stereochemistry of the process is we can see the process as a 2+2 cycloidation. So it means what we are doing actually is just taking a phosphorus carbon bond and carbon oxygen, and then we are just linking to form. They are just collapsing to form this heterocycle of 4 members. Okay, so as this can be considered as a 2+2 cycloidation, so this step has to follow also the rules of the 2+2 cycloidation. Which are those rules? So those rules are mainly that if we draw the orbitals that are involved in the process of a 2+2 cycloaddition would be, of course, the LUMO of one bond and the LUMO of one bond and the HOMO from corresponding to the other bonds. Okay, so we would have something this situation. If this would be the carbon, phosphorus, carbon, the oxygen. This would be the carbon phosphorus from the phosphonium salt, and this would be from the carbonyl. Okay, these are represented. It will be the orbitals involved in the 2+2 cycloaddition. Okay, so as we can see here, there would be like a bonding interaction between these two orbitals, but however, there would be a non-bonding interaction in this side. So this approximation is forbidden. Why? Because of course there is the same number of bonding interaction and non-bonding interaction. That is the reason why the approximation cannot be done just simply like this, but it has to be done just twisted in this manner. Right? You can see like this exactly. Okay. So now, if we draw now the disposition of the orbitals. So now the situation changes, and then we have bonding interaction here, 2 bonding interaction here, and also 2 bonding interaction here. So if we see here it would be something like this. Okay. So okay, we have said that the approximation of the carbonyl to the halide the carbonyl to highlight is controlled kinetically, and the steric hindrance has a special, has an important role in this case. So the stereochemistry, the final stereochemistry can be seen easily if we draw the structure of the approximation of both components. So for example, if we have here the two possibilities, so this would be the two possible approximations. So if this is here the highlight, the phosphorus carbon from the highlight, the carbonyl could come in this, from this, in this way, or either in this way. Okay. So from whenever one draw this this structure, one sees this structure, is very easy to see how here. So the bulky R2 group find the very strong steric hindrance with very strong steric hindrance with the phosphorus group. Okay, and here, however, on the other side, we have that the phosphorus has here an hydrogen, and in the opposite side, and then the R2 has an hydrogen. So then, therefore, here there is more steric hindrance. So then these two species would evolve in such a way, as we can see, we have seen previously. So there would be the attack, nucleophilic attack from the center to the carbon, and then the collapse to form finally this 2+2. The product of this 2+2 cycloadation, it would be something like this. PR3. Kinetic control of, so then give rise to the product, which is not as stable as the one we can get from thermodynamic control, and we can see here, for example, I forgot here one. We can see that this product, of course, has more steric hindrance than this one here that has an hydrogen, and then there is much lower steric hindrance. Okay, but finally, the final step, the rearrangement of this derivative give rise to the E to the Z, this being the mature product. Okay, which are the factors that can influence in this stereochemistry? So of course this is not a process. There are two different pathways. So it's not happening. It's not black and white. Can be also gray, and there are a lot of factors that impact that can make it a little bit more gray, or a little bit more white, or a little bit more gray. I mean, more to get more the E configuration or either the Z configuration. Which are the factors that that are important for the stereochemistry. So the factors that are important are of course, first of all, the stability of the halide, okay? So if we go back to the mechanism, to the whole mechanism, so of course, R groups are one group that stabilize this. So it's charged species. So R group in either here in the carbonic group or either in the phosphor group that stabilizes the plus and the minus charges will make the halide more stable, and therefore halide more stable will tend to rearrange in such a way that we give the most stable product, which is the one from the thermodynamically controlled process, and more reactive halide, more unstable, will give finally as a major product the Z product as the major, as a consequence of this kinetic control of the reaction. Of course, the stability of this halide is not only coming from these two different groups, but also it comes from the environment. So polar solvents, of course, interact better with charged species, then stabilizes even more the halides. Okay, and the presence of salts, the presence of ions, the same story. So the ions stabilize the charges in the medium and gives rise to more stable species, intermediate species. Also, what I would like to show you is like how is the influence, more concretely, the influence of these two different groups, because there is a table that is in the slide that you can find in the PowerPoint. It's here. So if now we call, so as we can see here, it's summarized very well the situation with the different substituent of the halide. Okay, if this, we consider this here the R1 group, this the R3, the R2. Okay, depending on the three groups. So of course, the preparation of the halide, we will need different conditions. So for whenever we synthesize halides that are not so stable, which are mainly whenever R1 so whenever R1 are, for example, aryl substituent, and R2 and R3 are allyl or H group. So then stronger bases will be needed. So as within lithium, or we have this derivative, sodium derivative of terbutoxide, potassium terbutoxide, will give mainly this cis, this Z, of course, what we have, the Z predominantly this Z stereochemistry. Okay, so whenever we have semi-stable halide, so the semi-stable halide will give a mixture of both stereochemistry, will be the Z and the cis, and this will happen whenever in the phosphonium there are groups of the phosphonium from the halide are, for example, still here aryl and then R2. Alkenyl, then benzyl group, also finally, the last situation we can have is like very stable highlight. This happens whenever we have here in this position we have acceptor moieties, acceptor groups, and this. So then we'll need for that will give rise. So this highlight will give rise to predominantly the is stereochemistry, and the needed base for the protonation of this center much more weaker, having sodium hydroxide, and this will take place whenever the R1 is aryl, for example, and with acceptor electron acceptor group as can be esters, sulfons, cyano group. Okay, so as example of this reaction, so this reaction Wittig is very important because, as probably you know, at least you should know, Georg Wittig was working here in this university and discovered this reaction in the 1953 and got the Nobel Prize in the 79. Okay, so the reaction, one of the first example that were published are shown here. So it's very straightforward reaction, but it was the beginning of a whole evolution that have been in this taking place with this reaction, with the Wittig reaction. This was, as I said, in the 1953. Okay, there are, of course, several modifications from this Wittig reaction. That one of them that are really important in the synthesis, in organic synthesis. One of them is the Wittig-Stock reaction. The Wittig-Stock reaction, in this case, gives rise to this product at the end, which has an halogen, a terminal halogen. This terminal halogen is very important. Why? Because it allows further functionalization of further growth of the molecule, and further functionalization of course. So the difference is like now is using this diiodo methane. So the phosphorus now attack diiodomethane, substitution of one of the iodide, then deprotonation to get this halide here that can react, attack here in the carbonyl group, and then finally giving rise this double bond plus the terminal halogen. Okay. Another example that is very important is the Wittig homologation. So the Wittig homologation, homologation reaction in general is a reaction that transforms the reactant into another species that differ only in one repetitive unit. Okay, so in this case, the repetitive unit is so what is happening here. So I will explain the mechanism. So we have this chloride derivative. We start from this chloride derivative. So phosphorus again, formation of the halide. So substitution of the halogen to give this phosphorus derivative here, this phosphonium. Then deprotonation of this carbon to give the halide. And then the halide can attack to the carbonyl to give here this product. Now, in the presence of an acid media, this compound can evolve, eliminating methanol, giving rise finally to this aldehyde derivative. As you can see, this is exactly the same. Well, is the analog to this region here, but only with one more carbon, which is the repetitive unit that I mentioned for the homologation. Okay, that give the name to this reaction. Okay, of course, in the following, once this reaction was discovered, so a lot of modification came just to try to force the reaction to go into one certain stereochemistry. So to instead of going mainly to the Z product, to force the reaction to go to the E product. So this is the case of the Schlosser modification. So the Schlosser modification, I want to show you the scheme of general scheme, and we'll go to the so the Schlosser modification, the scheme. So the reaction is quite more or less the same. We'll go to the deeper into details of the mechanism in the following slide, but it's finally it's exactly the same thing. So formation of the halide, so phosphonium, the reaction of the trialkyl phosphine to this reagent here. So and then the protonation of the center to give the halide is exactly the same thing that Wittig. Okay, in the Wittig reaction, but now the difference come here. So it's the use of a second equivalent of base, the strong base, which can be here, for example, phenyl lithium. Okay, so the use of another equivalent of base give finally predominantly the E product. Which is the reason for that? So let's take a look then to the mechanism. So the formation of the beta ions for the formation of the beta ions are exactly the same. So I'm not going to write the whole mechanism. It's exactly the same structure, and I'm going to start from the structure of the same scheme. I'm going to start from the structure of the beta ions. Sorry, this is hydrogen. No, I've changed the other groups. Sorry for that. So this is the beta ions, the same story. So we have this the reaction of the halide. So again with the carbonyl one from this phase and then from the other phase. Okay. So now, however, so we can see. So the difference is, of course, I have turned this time. I have turned here the phosphonium center. Okay, this carbon here. So we have the R. The R one is in this side now, and the other is here. Okay. So now the Schlosser modification use another one more equivalent of base. So and further deprotonate here this center. So they remove this hydrogen here to give rise to this species. And we have here Sorry. Okay, this is the species. These two dots, represent here of course the minus charge after the protonation with the base. And these two species now are in equilibrium. So these two species are in equilibrium. Of course, they evolve in such a way to reduce the steric hindrance as much as possible. So here, for example, we have the two bulkier groups, which are R1, R2, that are, of course, they have here this interaction. Therefore, this reaction is prefers to go in this way. The equilibrium is placed in this direction to give this less hindered species intermediate, and finally the protonation of this species here gives rise to the final product. So first of all is proton comes here, react of course with acid P+3 minus, and finally okay, this is, as you can see, so it's quite similar to the VTEC, it's just a modification. So that, but gives rise at the end, the main advantage is gives as a major product the E configuration. So an example of this reaction is here. So it's showing this slide. So for this, in this case, so it's using as a base using sec-butyl lithium at room temperature. Then of course it's necessary to add at low temperature, of course, because this is a very reactive species. At low temperature, the corresponding carbonyl group. Then again, the protonation, second equivalent now of sec-butyl lithium to get this equilibrium between beta ions, and then of course the source of proton at room temperature, which is in this case methanol, gives rise. Well, this is into the E configuration with a moderate yield, but if this reaction would have been done in other, using for example VTEC reaction, it would have been mainly the other configuration. Okay. The next olefination reaction we're going to see is the Horner-Wadsworth-Emmons reaction. So this is the reaction was used for use during for the synthesis of the phosphorus derivative that I have shown you before in my presentation. And instead of using halide, now what is employed is the use of a phosphonate. The phosphonate is this species here. Of course, also necessary to use a base. The phosphonate are much more nucleophilic than the halide, and so generally R1 needs to be electron withdrawing group, but it's true that this reaction also works whenever R1 is an electron donor. Okay. So for of course to carry out our Horner reaction, what we need is first of all to synthesize the phosphonate. The phosphonate can be obtained via a very simple reaction which is called Arbuthnot reaction. Which is only the reaction of this reactant whenever reactant again is an halogen, when X is an halogen, bromine, iodine. Of course, works always better. Is better leaving group the iodine, better than bromine and chloride, of course. And is the reaction at high temperature, so the temperature is 120, 140 degrees with triphenyl phosphite, trialkyl phosphite, which is this species now here. Three, okay, and so again, phosphorus has a lone pair here, so it can make a nucleophilic substitution here in the center, giving rise ethyl group. Okay, so we have one. A plus charge, and the halogen now can attack to this center, and come here. Reaction evolve to give finally okay, so this reaction is very nice because actually, so the triethyl phosphate is used in a huge excess, and yeah, but this is not a problem because at the end, so this reaction takes place quantitatively, and at the end it just can be pumped out, and then the purification it's quite straightforward. Therefore, the once we had the phosphonate synthesized. So now we can now carry out the reaction with a carbonyl group. Okay. I'm going to show you an example with this ester derivative. Okay, so first of all is deprotonation. So this the phosphonate, the same as was with the highlight. So this position here can be deprotonated again because it's especially the anion is stabilized by resonance. As we are going to see, I'm going to write here. So the reaction with base attack therefore here in the center, and we can get this these are the different resonance structure of this. Okay, so now okay, so this is this because of the stabilization. So the is because of this resonance structure is especially stable, and now the reaction coordinate of this multi-step reaction is going to change, and then now the formation of the beta ions is not going to be the rate limiting step. Is now it will be the next one. What I mean is, like, if we have before we had, if the situation before in our multi-step reaction was like this, so this was for the VTIC, so the higher activation energy was here in the first step. Therefore, the formation of the beta ions was a rate limiting step. Now we have a situation which is more like this. Okay, so it won't be the formation of the reaction of the with the carbonyl group. It will be the next one. So again, we have two possibilities. So it can attack one side like this or like this. Same story as with VTIC reaction. This is in equilibrium. Okay, so now is this is the formation of the corresponding beta ions, and these ones are these ones are specially stabilized because of it's possible. So the base, the counter ion of the base can stabilize, can form an adduct like this. So which is only the insertion of here, so the X is interacting here. This is this 6-membrane cycle here. This is responsible for the stabilization of this intermediate. Okay. Now again we have the formation of the cycle of 4 members as previously. Okay, and the formation, and this time in this reaction, so the formation of this cycle, of this intermediate, is the rate limiting step. So we have here, so it's like the situation with the black line here, in which so of course the intermediate is higher in energy. Why is higher in energy? Because now this intermediate here has a charge, and of course charged species they possess a higher energy. Okay, so this corresponding, so the pathway that drive the reaction in this intermediate, of course, gives rise to a higher stereochemical hindrance, and as all at the beginning in the first step is in equilibrium, so the reaction prefers to follow the other pathway, which is the thermodynamically controlled reaction pathway. Okay, so finally, rearrangement of the bonds gives rise to the formation of the last product. This is the E, and this is the Z, and this is the major. Okay, and of course the side product from this rearrangement is phosphate, so would be with a base counter ion. Okay, this derivative here, this phosphate is water soluble, which is very nice because during the workup, just with an extraction, we can just remove from the crude of the reaction, and then get the purification gets better. Sometimes the corresponding derivative from the Wittig reaction, which is, if I haven't mentioned before, is R3. This one is this compound here is too organic to be removed from only with water, okay, from an extraction, and therefore, yeah, most of the time necessary to remove it with a column chromatography. Okay. So an example of this reaction here. So we have seen the final product of final result with the compounds in my presentation before, but I also would like to show you a synthetic route that the Professor Bunz developed some years ago, which is you can find in this slide here. Okay. So first of all, the reaction starts from this paraphenyl derivative. We have a iodination reaction, so it's a reaction that happen quite selectively in these two positions, so position also to the methyl group. Then we have is bromination with N-bromosuccinimide. So this is a radicalic reaction that take place, of course, only in the benzylic positions. Reaction that is very nice. Then formation of the phosphonate, Arbuthnot conditions, so 140 degrees, and quantitatively it's possible to obtain this phosphonate. And as I said again before, pumping out the excess of triethyl phosphate, we can get a clean final product. Okay, now the reaction with a carbonyl group, which is this para-formaldehyde derivative, and with this base potassium terbutoxide, is possible to carry out a double Horner reaction in two positions, and without the other halogen are not interfering at all. So this allowed finally in the last step with a Sonogashira cross-coupling to get these cruciforms. This is the name that Professor Bunz gave to this derivative long time ago, that they have special properties have been used for a variety of in a variety of fields, and they are also kind of they are very highly fluorescent as well. Okay. So something that I haven't mentioned now is like, and it's important to remark, is so this configuration Z or E, of course, give in NMR different J coupling constant. Okay, so for example, in this derivative here is shown the NMR spectrum of this only. J constant of 16 Hertz could be fine. J constant of 16 Hertz are typical for E configuration. On the other hand, J constant of approximately around 8 Hertz are characteristic for the Z. Okay, this is something that is quite important, because allows us finally to identify what configuration we are getting after the Horner olefination reaction. Okay, and the coupling is actually the signal from the double bonds are these two here. Okay, so these are from here, from this proton, the proton from here, and proton from here. Okay. So the Horner reaction, the Horner reaction depends really a lot on the structure of the phosphonate. Okay, so whatever modification we will make to the phosphonate structure will modify the stereochemistry of the process. One important modification of the Horner reaction is the Steele-Gennari modification. This is the general scheme. Okay, so the Steele-Gennari modification uses in the phosphonate a derivative which has this group here with a fluoride, with a trifluoro methyl group, as in so the terminal, and instead of ethoxy group is trifluoroethoxy group. Okay, and use as a base this potassium. I'm going to write the name here. Bis trimethyl silyl amide. Something also very characteristic from this modification is the use of an ether chrome. So we'll see. I'm going to enter in details now in the next slide. But one thing that is very important, instead of giving, as the Horner reaction was giving the E configuration as the most predominant, now in this case we obtain the Z product. Okay, so taking a look to the, let's take a look to the mechanism. The formation of the phosphonate is exactly the same, and the deprotonation. So the reaction until the deprotonation is the same as the Horner one, and so I'm going to start from this step here. From this species, so we have here deprotonated. Okay, this is stabilized, of course, by resonance. Then now reaction with a carbonyl group. Two possibilities, two approximations are possible, as always. Okay, so now, so the change now, the modification is coming here. So if you remember in the previous, in the Horner reaction, we had an intermediate what was in which the counterion from the base was quite important. Now in this modification, we are in this base, the potassium is the counterion of the base. So it was the counterion could, the same as it was doing for the Horner reaction, so stabilize this beta ions type derivative in such a way. However, now in this case, what we are using is an ether crown, and I don't know if you know, but ether crown are known to be very reactive with potassium, with ion. We ion such a potassium. So then this what is doing is extracting, removing this, preventing the potassium here to interact with these two oxygen here. So in such a way, so we have the so this is the ester crown, and can interact, as I said, then with the potassium, and then is extracting, is removing, preventing the potassium to interact, and therefore to stabilize these two species. Okay, so then these two species are not so stable. So then this changes completely the whole reaction coordinate, and this time the formation of these beta ions will be the rate limiting step. The mechanism evolves the same as the Horner reaction from this point. then finally rearranges to give the final product. And this will be the mature product. Okay, so this is the rate limiting step, and therefore we have a highly reactive species. Therefore, it will react very fast. Then we are talking about kinetic control of the reaction. So the stereochemistry, we can explain it as a function of the steric hindrance, which we can see very clear whenever again we will draw the structure, the approximation for the 2+2 approximation. Okay, 2+2 cyclization. Sorry. So okay, the examples, some examples from this reaction are shown here. Okay, so as we can see, of course, this is not always like black or white, so it gives a mixture of configuration. So E, Z, and E, but mainly predominantly is of course the Z product, as we have seen. So the conditions are in both reaction the same, using the base we have explained at the beginning and previously, and then the ether chrome. Okay, so I think so we are going to stop here today this lecture. So I hope you have understood quite very well. Feel free to come to my office to ask if you have any question, and I hope you understood most of what I explained today. And thank you for your attention.